Alright guys, welcome back to Underground Science, and in this video we'll be looking at diamagnetism. Alright, so pretty much diamagnetism has to do with studying the electrons in the last energy level of an element. Alright, so pretty much just remember that if an element's last energy level, if there are no unpaired electrons, then that means that element is diamagnetic. Alright, so that's the simple overview definition. If an element's last energy level, if it has no unpaired electron in its last energy level or subshell, right, that we'll see later, it's going to be identified as diamagnetic. Alright, and so with that being said, let's go ahead and just choose two examples that we can identify and work with that we'll see later if it's a diamagnetic element or not. Alright, so let's go and do beryllium and magnesium. Alright, so let's go and get started. So first, let's go and write down the electron configuration for beryllium. Right, so again, go ahead and check out my electron configurations video if you haven't already. Alright, so 1s2, 2s2, and we're done. Okay, so 2s2, and now let's go and draw the electron configuration diagram, right, or the orbital diagram. So for that, let's go and write out our first energy level, our 1s, and then our second energy level and our s subshell, our s orbital. And as we can see from electron configuration that we can only fit 2 electrons in the 1s orbital. So we're going to draw a positive 1/2 spin quantum number and a negative 1/2 spin quantum number. In our second s orbital, we can still only fit 2 electrons. So we're going to draw a positive 1/2 spin quantum number and a negative 1/2 spin quantum number. Alright, so here we see that in our last energy level and subshell, in our 2s orbital, we have no unpaired electrons. We have only paired electrons, right? These are a pair of electrons. One spinning in the positive 1/2 direction, one spinning in the negative 1/2 direction. Alright, so one electron here is spinning in the positive 1/2 direction, the one that looks like that, and one electron is spinning in the negative 1/2 direction. Okay, so that means that beryllium is diamagnetic. Alright, so that means beryllium is diamagnetic. And what that also means is that since we have 2 electrons spinning in the opposite directions, it kind of cancels its magnetic field. So that means that we have diamagnetic elements don't really get pulled into an external magnetic field. They're very weakly attracted to an external magnetic field. Alright, so let's go and write that down. So we have beryllium, that's diamagnetic, and we said that diamagnetic means that it's not going to really get pulled into an external magnetic field, right? So if you put a magnet, it's not going to really be attracted to an external magnetic field. So not very attracted to an external magnetic field. All right, so that's pretty much what diamagnetism means. All right, so if someone says that, all right, this is a diamagnetic element, you know that what they mean is that in the last energy level, right, our 2s in this case, and the s part represents the orbital, right? If there's a 2p, we'd look at the 2p orbital. In our last energy level, we have no unpaired electrons, then you know that we're talking about a diamagnetic element, and we know that a diamagnetic element is not very attracted to an external magnetic field, all right? So we're talking about magnetism here. All right, so that's pretty much it. Just look at the spin quantum numbers. If the last energy level we have no unpaired electrons, meaning one electron is spinning up in the positive 1/2 direction, right, and one electron is spinning down in the negative 1/2 direction, or the negative 1/2 spin quantum number, then we know that both those electrons are kind of going to act like they're canceling each other's magnetic field, all right? So you can think of it like that, and then just know that diamagnetic elements are not really very attracted to an external magnetic field, all right? Just remember that and we'll be good to go. So let's just go and look at another example, right? It's going to be the same exact concept. We're going to look at magnesium. Okay, so magnesium, first of all, our first step is to write the electron configuration. All right, so let's go and follow the step-by-step process. So we're going to write the electron configuration. So 1s2, 2s2, right? And then we go up, let's just go and look for reference. Sorry about that, 1s2. Then we have 2s2, which is beryllium's electron configuration notation. Then we have 2p6, right? 6 electrons in our 2p orbital. So 2p6, and then we have our 3s2 orbital. And we have reached magnesium, right? So our 3s2 orbital. So next step after you write your electron configurations is to draw the electron configuration diagram, right? Or the orbital diagram. So now we're going to draw the orbital diagram. Orbital slash electron, since say config to save time, electron configuration diagram. All right, and to do that, we just list out the energy levels. I mean, I like to list it out first, and then we can go and draw it just quicker, I think. So let's just go and write our 1s, our 2s, our 3 different subshell orientations, right, that we found out in our magnetic quantum numbers. I mean, in our quantum number video via our magnetic quantum number. And then we have our 3s orbital, right? And remember, energy increases as we go up in energy levels. Okay, so energy, I'm just going to write it like that. Energy is increasing. All right, so let's go ahead and label it real quick. So our 1s orbital, 2s orbital. As a whole, this is our 2p orbital, right, with our 3 different orientations. And then we have our 3s orbital, sorry about that, 3s. Now we have to go and look at each energy level and see how many electrons can fit in each energy level slash orbital. So our 1s energy level, or 1s orbital, I should say, can only fit 2 electrons. So we're going to go positive 1/2 spin, negative 1/2 spin, quantum number, right? 2s orbital, again 2 electrons. 2p orbital, we have 3 different orientations. Each subshell orientation can hold 2 electrons, so 6 electrons. And here we follow the Hund's rule, so make sure to go and check out my Pauli exclusion principle, off-bob principle, and Hund's rule video. But since we have 6 electrons, we can go and fill it up, right? So 3, 4, or 5, and 6. And last but not least, we have our 3s orbital that holds 2 electrons, so 1, 2. Again, we see here our very last energy level holds 2 electrons, and it has no unpaired electrons. It only has paired electrons. One that is spinning in our positive 1/2 direction, our positive 1/2 spin quantum number, right, spinning up. And we have 1 electron spinning down as a negative 1/2 spin quantum number. And this means, again, that we have 2 electrons spinning the opposite direction. So it's going to really kind of cancel out each other's magnetic field almost, you could say. And what that's going to lead to is that we're going to identify magnesium as a diamagnetic element because it has no unpaired electron in its last energy level. And we found that out by drawing our orbital slash electron configuration diagram. But remember to begin with writing an electron configuration notation first. All right, so magnesium is diamagnetic. All right, so and again, what this means is that magnesium will be very weakly attracted to an external magnetic field and will not get pulled into an external magnetic field. So again, not very attracted to an external magnetic field. All right, so that was our 2 examples for diamagnetism. And the next video, we'll look at 2 examples for paramagnetism. And so that way we'll know what diamagnetism and paramagnetism is. So we'll know how to identify diamagnetic elements and paramagnetic elements. All right, so I really hope to see you guys in my next video where I talk about paramagnetic elements, and we'll follow the same process there, except we'll see something different in paramagnetic elements. All right, in terms of our electron configuration and talking about paired and unpaired electrons. So hopefully I see you guys there, and so see ya and stay safe.